Alright, hello. We are going to continue our discussion of Chapter 15. So we've talked about kind of the properties of sound and how to calculate speed and the wavelength and what a sound wave is. And now we're going to look at the main application of sound, which is the physics of music and how we can take those sound waves and make them into something that we like. So let's first talk about sources of sound. So sound is produced by a vibrating object. So something needs to oscillate back and forth in order to produce sound, and there's lots of ways that you could do this. So with your voice, your vocal cords vibrate, and that produces that change in pressure, which causes sound waves. For a brass instrument, your lips would vibrate on the mouthpiece, which then produces the sound. For wind instruments, like clarinets and saxophones, the reed will vibrate. For stringed instruments, it's a string, like a guitar. So a lot of these instruments work kind of the same way. We have this oscillation, but we're going to look at closed and open pipes as a way to look at where resonance occurs and how sound travels. Okay, so for most instruments, the length of the tube determines the frequency. So like on a flute or a clarinet or saxophone or even the string on a guitar. And so the mouthpiece just causes the vibration, but it's the length of the instrument itself that determines the frequency. So we've got two different kind of instruments that we're going to look at. So a closed pipe resonator is a resonating tube with one end closed to the air. So closed pipe, it's in water as you can see here, or something like that. Okay, so we can use closed pipes to produce standing pressure waves. So we have a tuning fork over the top of the pipe, so as you can see here we've got this tuning fork, and we're going to hit it, and then it's going to create sound waves that are going to travel down the tube. Okay, so we can have this tuning fork producing a sound wave, and it's going to travel down the tube to the water because this is a closed pipe, and it's going to hit the water and reflect back up. So if the reflected wave reaches the tuning fork at the same time that the tuning fork produces another wave, then the emitted and the reflected waves are going to reinforce each other. We talked about constructive and destructive interference, so we would say that this is constructive. And so if this happens, then this produces a standing wave, and we've achieved resonance. Remember, we talked about resonance is just the addition of these waves, and this time they're adding together because they are reinforcing each other. Okay, the other type of resonator instrument we can look at is an open pipe resonator. So this is a resonating tube with both ends open that also will resonate with a sound source, just like the closed pipe. And in this case, the sound wave reflects off of an open end. So the pressure of the reflected wave gets inverted, and the high pressure wave becomes a low pressure wave. Okay, well, let's look at the difference in resonance lengths for open and closed pipes. Remember, resonance is where those waves are going to add together. Okay, so we have these standing waves. So a standing sound wave in a pipe can be represented by a sine wave, and this represents the air pressure or the displacement of the air particles. Remember, sound waves, we need this difference in air pressure and moving of the air particles in order to have sound, which is why sound won't occur in a vacuum. So standing waves can have nodes and antinodes, and if you remember this from the last chapter, so if we just draw a wave, okay, then our nodes are regions of mean atmospheric pressure, where there's really no displacement. And so we would put nodes at these points right here. So antinodes are where the pressure oscillates between minimum and maximum, or the most displacement. So here is the most displacement positive, here's the most displacement negative, and we could go on like that. Okay, so we've got nodes and antinodes, which is very similar to what we had in the previous chapter. We were just talking about waves in general. Okay, so let's look at resonance frequencies in a closed pipe. So the shortest column of air that can have an antinode at the closed end and a node at the open end is 1/4 of a wavelength long. Okay, so our shortest pipe could be 1/4 of a wavelength long. And as the frequencies increase, additional resonance lengths are found at half wavelengths from that point, or at half wavelength intervals. So what this means is that we can have columns of length 1/4 wavelength, because that had to be our minimum, and then half wavelength intervals from there, and those will all be in resonance with the tuning fork. So we could have 1/4 wavelength, 3/4, 5/4, 7/4, etc. So the measurements of spacing between the resonances can be used to find the velocity of sound in air. And we'll look at some problems on how to do that. Some examples of closed pipe resonance instruments would be a clarinet or like a seashell, if you've ever listened to like a conch shell. And it sounds like the ocean. Okay, so here's some examples of the waves and the resonance at different intervals of this shortest wavelength or shortest distance. Okay, so let's look at resonance frequencies in an open pipe. Here, the shortest column of air with nodes at both ends is 1/2 of a wavelength long. And so as the frequency is increased, we're still increasing it by 1/2 of a wavelength, just like we did for the closed pipe, but because we're starting at 1/2 of a wavelength instead of 1/4 of a wavelength, our intervals are different. And so columns of length, 1/2 wavelength, wavelength, 3/2, 2, so adding 1/2 every time will be in resonance with the tuning fork. So here we have still increases of 1/2 a wavelength like we had with the closed pipe, but we're starting at a different point. Some instruments that represent this would be flutes and saxophones, which I thought it was really interesting that saxophones would be an open pipe and a clarinet would be a closed pipe. But remember, it's more the length of the tube that influences this versus the way that we create the vibration. And even though they both use reeds, their body shapes or their tube shapes are very different. Okay, so the wavelength for the open is 1/2 as long as the closed, right? Because we're starting in these different spots. And so here's just some differences between closed and open pipe resonance. But the frequency for open is 2 times as high as closed. So the wavelength is 1/2 as long, but the frequency is 2 times as high. And that makes sense because wavelength and frequency are related in that way. And we can use those to find speed. Okay, so we've been talking about open and closed pipes. Now let's talk about strings. So waveforms can vary in shape based on how they are produced, whether it's with a reed or a tuning fork or a string. So a string is clamped at both ends, so there's a node at each end. And this is kind of like an open pipe. The resonance frequencies are whole number multiples of the lowest frequency. So the speed of the wave on the string depends on the tension. Remember, you can tune your guitar by changing the tension on the strings, and also the mass per unit length. You can have different weights of strings. That's probably not the right term, but they can be, different tension and different mass. And so you would tune your guitar by changing the tension. So the tighter the string, the higher the frequency, and you can tell this if you've ever plucked a guitar and as you tighten, you can hear the frequency. Okay, so with all of these instruments, we also want to talk about sound quality. Okay, so tuning forks produce simple harmonic waves. The human voice and instruments, though, produce a much more complex wave. And so the timbre, or the tone color, is this difference between the two types of waves. And the difference between a simple harmonic and a complex. Okay, so let's look at these harmonic and some fundamentals of those things. So a fundamental is for a musical instrument the lowest frequency that will resonate. We call this F1. A harmonic are higher frequencies, which are odd number multiples of the fundamental. So we start at the fundamental, and we can go in odd number multiples from there, and those would be harmonics. The addition of harmonics gives an instrument its unique timbre, and so that's what makes music and instruments, more interesting than this just simple wave. So the sound spectrum then is a graph of the amplitude of a wave versus its frequency. So now frequency is how many waves per unit of time, and amplitude is going to be its height or its difference from equilibrium. Okay, so let's talk about, in relationship with these complex and these simple waves, consonance and dissonance. Okay, so we can play a chord, which are several pitches played together, and if you play piano, well, really any instrument can play a chord. It just seems more commonly taught with a piano. If you have dissonance, this is an unpleasant set of pitches. And consonance is more of a pleasant combination of pitches, and so your ear can pick up whether it sounds pleasant or unpleasant. So according to Pythagoras, pleasing sounds result when strings have lengths in small whole number ratios. So this is why pitches also have small whole number ratios. Okay, so we've talked about chords, and let's talk about musical intervals. So we can have two frequencies related by the ratio 1 to 2 can differ by an octave. And the fundamental and its harmonics, remember the lowest frequency and then odd number multiples of that, are related by octaves. So in other musical intervals, pitches may be close together. You could have a major third, a major fourth. It doesn't always have to differ by an octave. And with all of this comes beats. So if you're in band and you're trying to tune the whole band, you've probably heard this before. So a beat is an oscillation of wave amplitude. And this is caused when two frequencies that are nearly identical interfere to produce high and low sound levels. So you will hear these when your band or all the instruments that are all being played together are close to in tune, but they're not quite there, and you can really hear it. It sounds like this wave thing. So the frequency of a beat is the magnitude of the difference between the frequencies of the two waves. And so if you have, a wave at one frequency and a wave at another frequency, the difference between those, that's the frequency of the beat. You want it to be 0, basically. That would mean you're in tune. Okay, so we play all these instruments and we do these chords and get them in tune, and now we want to reproduce the sound through a recording or a speaker. So a good stereo reproduces all frequencies equally, because if, for someone singing, they have a wide range, and you want to be able to reproduce all those frequencies so that it sounds just as good as it would live. And so this is usually 20 to 20,000 hertz. Remember, hertz is a unit of frequency. A telephone only transmits information in the spoken language, which ranges between 300 to 3,000 hertz, because you don't really need to do anything other than that. And if you reduce the number of frequencies, this reduces the amount of noise, and so it makes for much better quality within that range for a telephone. Okay, so we've talked about different instruments, open pipe, closed pipe, how to have resonance, then different definitions going along with music, such as intervals and chords and beats. And so now we're going to do some practice. We're also going to do some practice problems in class as well. All right, have a good day.